Hello and welcome to another LeetCode video. In this problem we're going to be doing find critical and pseudo-critical edges in a minimum spanning tree. And this is kind of a hard problem, and honestly the hardest thing is like the time it takes to do it and the debugging. It's very easy to make errors, but you're going to need to know union find, and you're going to need to know Kruskal's algorithm for the minimum spanning tree. I will go over the algorithm for the minimum spanning tree. It's not that hard, but I'm not going to go over the union find because that would just make the video too long. So I would suggest, like, before starting this problem, learn what the union find is. Okay, so you're given a weighted undirected connected graph with n vertices. Essentially, I'm just going to show you I'm not going to read all this. I think it's like pretty easy to understand. So essentially, they give you a graph with n vertices and they give you a bunch of edges, and all of these edges have a left and a right and an edge weight. So for example, this 0, 1, 1 means there's an edge here, and it is weight 1. I also don't really know why they have like this kind of thing. It's not the best. So I think what we're actually going to do is, instead of these, let's just write in our own values. So for 0, 1, this is weight 1. So we're going to write 1 here. Then for 1, 2, that is weight 1 as well. And then for 2, 3, it is weight 2. And for 0, 3, it is weight 2. And then for 0, 4, it is weight 3. For 3, 4, it is weight 3. And for 1, 4, it is weight 6. Okay, so we are going to re-go over this, how to actually construct a minimum spanning tree. But first, we're going to go over so we want to return the critical and the pseudo-critical edges. So the critical edges need to be on the left, and the pseudo-critical edges need to be on the right. So we're going to define critical and pseudo-critical edges. So a critical edge in a minimum spanning tree means it is in every tree. And a pseudo-critical edge it can be in a tree, but doesn't have to be. And so they show you, this is not the way we're going to do it, but they show you every single possible minimum spanning tree. So if you look, like an edge like this is in every single one. So it's a critical edge. Without it, you cannot make a minimum spanning tree. So this 1, 2 edge has to be in our answer, I believe. And so, yeah, it is. And the distance, I think the reason to do it is because it's the index. So you want to give the index of this edge. So this 1, 2 edge is index 1. So that's why 1 is in the output. And let's see what other edge is in everything. So this edge is also in everything. This 1, 0 edge. And this is index 0. So 0 and 1 have to be in every single spanning tree. And then every other edge, so we're going to just draw those in. So these two have to be in there. And then every other edge that's in any tree is optional. It can be in there, but it doesn't have to. And so what edge is that? So that's the 0 to 4 edge, which is right over here at index 3. And then there is also this edge over here, this 2, 3 edge at index 2, and so on. So you kind of get the point. Like, every critical edge is in every single tree, and a pseudo-critical edge just means it can be in a tree. So now let's just go over how we make a minimum spanning tree and like the algorithm we're going to use. And so let's actually go over this one as well. So in this one, there's only one. A minimum spanning tree. So all of these are length 1. So let's go over this one first of all. So what does a minimum spanning tree mean? Let's just define that, right? A minimum spanning tree. So MST. It means that every edge is connected. Every vertex is connected to every other vertex with the minimum possible cost. Okay, so every vertex is connected with the minimum possible cost. So here, every edge is length 1. So essentially, you could see that if you just get rid of one of these edges, like let's say we get rid of this edge over here. Let's say we get rid of this edge. You can see if we just get rid of this edge, everything is still connected, right? It's possible to get from 1 to 2. You would just go around this way. So you need 3 edges for this to be connected. You can get rid of any one of those. It doesn't matter. So there are 4 minimum spanning trees here, and let's just draw those out. So they're going to have 0, 1, 2, 3. That is one of them, right, with this edge missing. And then you're going to have 0, 1, 2, 3 with this edge missing, and then so on, right? So you're going to have 4 of these with one edge missing, and there's 4 different edges. So 0, 1, so we can have this edge missing, 0, that edge missing, and what's the last one? It's going to be this one on the right, right? So that's the last one. And all of these minimum spanning trees, actually, I didn't want that, so I want this instead. There you go. So these are all the different ones you can make, and all of these are length 3, right? The cost to build them is 3 because each edge is 1 here. So let's go over the algorithm to calculate the minimum spanning tree first of all. And we are going to do that by using this. So let's just copy this thing right here. Yeah, let's copy that down and let's construct a minimum spanning tree from this. Okay, so I'm going to show you how to do this. And let's actually draw out the nodes. And like I said, there are a few here, but let's just show how to make one that's guaranteed to be a minimal spanning tree. So first we're going to draw out all our edges, or all our vertices. 2, 1, 4. And then we are going to draw out all of our edges, but we need them sorted. So let's do that as well. Okay, so our edges, I think they are already sorted here actually for convenience. So perfect. So essentially what we're going to do is we are just going to use the smallest edge we have to connect components, but we have to make sure they aren't connected already, right? So for example, if this is connected, we wouldn't want to make an edge here because this doesn't do anything, right? They're already connected. So the algorithm for Kruskal is you're essentially using all the edges you have, smallest to biggest, until everything is connected, and you're going to check if everything is connected with the union find. So with the union find, whenever you call union, it should give you like a true or false, meaning it was already connected, or you connected it now. And then you can just count up how many unions you have. And so if you think about it, if everything's connected, like here, let's just say it wasn't connection. So for 5 nodes, there should be 4 connections. So you can just, every time you have a successful union, you can just count up your connections, and you're looking for n-1 connections, meaning everything's connected. But let's go through these edges. So 0 to 1, length 1. So we're going to obviously use that edge. That's a cheap edge. Okay. 1 to 2, length 1. Okay. Sounds good. These aren't connected yet. 2 to 3, length 2. Okay. That's a cheap edge as well. 0 to 3. So this 0 to 3 edge, you're not going to want to use this one, right? Because these are already connected. All of these are already connected. So we're going to skip that one. And then 0 to 4, length 3. And here we have a minimal spanning tree, and you could see this should be one of the ones. Yeah, so there's a few different ways you can make it, but this guarantees you to build one minimal spanning tree, and it's guaranteed to be, if there's only one solution, this will be it, and if there are more, this is one of them. So that's how you build a minimal spanning tree. You essentially just look at the edges, smallest to biggest, and you just keep using union find to connect your stuff. Okay, now how do we do that along with this critical and pseudo-critical edge? And the way we're going to do that is you take your edges and we're going to append an index to the end of them. So they're not necessarily sorted. So we're going to append an index at the end of them because we need that index for the output. Like, let's say we have to sort these. We want to know where those edges were. So what we're going to do is we're going to take all our edges. Let's write that down. Take edges, add index variable to the end, then sort them by the cost of the edge. And the cost of the edge here is this second value here, right? It's like left, right cost in this example. So here it is. It's AB weight. So we need to sort them by the weight, and we're going to use the cheapest edges first. And then we're going to need to loop. So let's write that down. Loop through all edges. Then for every edge, what we need to do is we need to consider, can it be critical? And how are we going to do that? And so the way we're going to do that is we're going to have a helper function that's going to calculate this MST for us. And the way we're going to do critical, so critical means without it, if if this is a critical edge, let's say, without it, if you say I can't use this edge, your minimal spanning tree will either not be complete, right? Means all your nodes won't be connected. So you might have a situation like this where you just don't have everything connected, or it will be connected, but it will cost more. That's what critical means. Critical means it has to be in the tree for it to be a minimal spanning tree. So if it's critical, we are gonna run, we're going to have a helper function to do this, to calculate the MST, run MST calc or whatever it's called, and ignore that edge. And then we have two cases here. So case A, or we have three actually. Case A, we can't connect everything. Case B, our MST is more expensive. And case C, MST is the same. Now let's go over what all of those are for all of these cases. So if we can't connect everything, that means that we needed this edge to connect everything. So it was a critical edge. So if we can't, it's critical. So we're going to check mark meaning critical. Okay. If MST is more expensive, it also means we needed this edge to make the MST. Like we had to have it to make the MST. And if MST is the same, means it's not a critical edge. Like we didn't need it, right? We made an MST without it. It's all good. Okay. So that's our case. So if it is critical, so we're going to write that here. If it is critical, add to critical. And if it is critical, it can't be optional, right? So there were critical edges, and then there were like pseudo-critical. The pseudo-critical means you can have it, but you don't have to. So if it's critical, it means it can't be pseudo-critical, right? So if it's critical, add to critical. Otherwise, check for pseudo-critical, because it can be that as well. And so how do we check for pseudo-critical? Let's remember what pseudo-critical means. Pseudo-critical means it can be in there to make a minimal spanning tree. So for critical, we're just going to try to not have it and see, like, is our MST fine? And for pseudo-critical, we're going to write it over here. What are the checks we need? So checks for pseudo-critical. Like, how do we determine? So pseudo-critical means we can have it. So what we're gonna do is we're gonna force the edge, meaning we're gonna say we have to use that edge in our MST. We're gonna have to use it, right? Because we are seeing, is it fine to use it in an MST? And if it is, then it's a pseudo-critical edge. And then what are our cases here? So once again, we can't connect everything, right? Like, I don't think you're ever gonna have this. I feel like there's no way to force an edge, assuming there was an MST. I think you can't have this. I'm pretty sure. But in a ignored edge, you definitely can, right? Because, like, let's say your edges look something like this, you know, and this is your edges, and then you cut out this edge. But I think if you force an edge, you're always going to have. So I think you don't actually have to check for this. I think you're always going to be able to connect it. I think I might have checked for it in my code, but it seems redundant. But either way. So our other case is our MST can definitely be more expensive. And so if our MST is more expensive, that means it's not pseudo-critical. And then otherwise, MST is the same. It can't be less expensive, right? Because by definition, MST, once we calculate the MST, that is the cheapest we can have. So we can't have anything cheaper. So if it's more expensive, it is not a pseudo-critical edge. And if it's the same, it is a pseudo-critical edge. So essentially, our logic will be check for critical. Actually, sorry. Our logic will first be sort. We can write those steps down if you want. So it's going to be sort edges and keep index, then calculate MST, then for each edge, use helper to A, check for critical, B, if not critical, check for pseudo. And that's essentially what we were doing. And the nice thing is that if you look at our constraints back up here, our constraints are really small, right? So our edges length is like 200 squared, which is like 4K or something. I mean, it's not that small, but essentially we can have an n squared solution, and I don't think you can make anything more efficient. So you can just compare every edge to every other edge, which would be n squared. And so that's what we're doing. We're sorting, we're calculating the MST, and then we are, for each edge, using the helper to check if it's critical. If it's not critical, check for pseudo-critical. Obviously, I can't do like a dry run of this because this gets really big really fast. But that's essentially the things you need to know. You need to know union find. You need to know MST, which I just talked about how to calculate it, right? You just sort your edges and you just go greedy with picking the cheapest edges you possibly can without your stuff being connected. And that's pretty much all you need to know. So let's go over the code now. And here it is. So we have our union find. This is just a standard union find on LeetCode. There's nothing crazy. Yeah. So then we have our actual function, like our actual solution here. And so we have our helper function, and it's going to include a couple things. So it's going to include n, which is the number of like arguments you have. You probably don't even need this because it'll always be n, so I guess it's like not really needed, but I have it in here. And then we have a ban, and ban means the ban is we're going to check for our included edge, right? So sorry, not included edge, our critical edge. So if we have a ban, that means we're checking for a critical edge, and by default, our ban and our force is going to be, or our include is going to be -1. Yeah, because if you look for ban here, I believe. Did I use it? Yeah, I did. Here it is. So actually, sorry. Yeah, so for ban, what I ended up doing was, I'll get into it, but essentially, yeah, you're going to pass in an index of an edge that is going to be banned. And include means you're forcing the edge. And so here is our first condition. So our first condition is if include does not mean is not -1, we need to force the edge. So if we force the edge, this is how we get the two. This is like the left and the right of the edge, right? It's going to be an index essentially. And so if we're forcing the edge, then we need to make a union between the two nodes that edge connects, right? So we need to make a union between the two nodes that edge connects if we're forcing it. This is a pseudo-critical check. And then we're going to also add that weight to, so this weight is going to be like the weight of the MST once we're done. And so we're going to need to say, okay, we're gonna force that union, and then we are going to add that to the weight. Otherwise, let's just make the weight 0. And so for connections, it's the same thing. Connections is 1 if include is not -1, right? So if we include an edge, that means we have one connection. So this connections is going to be used to check how many connections do we actually have at the end. And so now we just loop through our stuff, and if we are banning something, meaning this is our critical check, right? So if we don't want the critical edge, we're just going to continue, right? So like if we say, okay, we want some edge to be banned because it's critical, so we want to try to run an MST without that edge, that's this case. And we don't have to check for this include, because when you already made a union, you can't make a union twice and union find, right? It'll just give you false. So we don't have to check for that. But otherwise, if we made a successful union, let's add to that weight and let's add the number of connections. And yeah, I think the reason I had it is because I just had a generic Kruskal function, because essentially your code for pseudo-critical and critical and the original MST is almost the same. So I just made a helper function with a few variables to like save like 20, 30 lines of code or something. Okay, so essentially at the end, you want to say you want to return your MST if you need to make sure that you have enough connections, right? And so if you have 100 nodes, you need 99 connections to make sure everything is connected. So we're going to return the weight if we have enough connections. Otherwise, we're going to return infinite. And then we're going to check that weight to make sure, like, is our MST valid? And so now our actual code here. So like I said, you want to append the index to all of the edges because we're going to sort them later. And the way you sort them is you sort them by an index. And so because it's like, because the edges are like left, right, weight, and then index, you want to sort them by the weight. So that would be x equals 2. And then finally, you get the min weight, which is, so this is the MST. So this is the MST with nothing banned, right? So -1 is going to be our default for nothing banned, and -1 is going to be our default for nothing auto included. Then we have our critical and our pseudo-critical array. And now for every single edge, we're essentially checking if it's a critical or a pseudo-critical edge. So to check for a critical edge, we're going to give it n again. Like I said, we can probably take this out. Yeah, because it's always n. So if we want to, I think we can. So let's actually do that. So let's just, because we have n here anyway, right? Like we have access to this n. So we can get rid of that. Yeah. And let's actually not even pass that in. Okay. This was super annoying to debug, so hopefully it doesn't break anything, but we'll see what happens. Okay. So essentially what you're doing is you're checking for a critical edge by giving it an index, and you're saying, okay, for this critical edge, let's ban this edge, right? We're passing this index into ban. And then if the Kruskal of this is greater than min weight, that means that when you took out that edge, the Kruskal was bigger. And so if the Kruskal was bigger, that edge is critical, right? Like, because we had our minimal spanning tree with that edge over here, and then without that edge, if it was bigger, or if it wasn't connected, which would just give you an infinite here, because I just have, like, if you don't have enough connections to turn infinite, then that is a critical edge. Otherwise, and remember, if it's a critical edge, it can't be a pseudo-critical edge. It's one or the other. So you check for critical first, then you check for pseudo-critical. And for pseudo-critical, same kind of thing. Now for band, you write -1, and for included, you write 1, or sorry, the index, meaning that this is a forced edge, right? So it's a forced edge, and we're going to need to add its weight and force a union find here. Okay, and then the same kind of thing. So for a forced edge, you need to make sure that your weight, your MST weight with that forced edge, is the same weight as your optimal MST, meaning that edge can be included, but it doesn't hurt your answer. So if it is that, then we can append it, and then edges I3, that's I think the index, yeah. So because it, like I said, it's left, right, weight, and then index. So we want the index, and that's why we needed to store the index originally, because we're going to sort our stuff. And it's super cheap to sort our stuff, right? Because we only have like 200 edges, but our stuff is like this is like an n² thing. So sorting is basically free here. So let's try to run that. So hopefully we don't run into any errors. We didn't. And you can see it's reasonably efficient. But yeah, I think this problem is just, I don't know if you can come up with like a solution in a, like, you can come up with a solution, but I don't know if you're going to be able to like come up with a solution and code it up. Like if you were just asked, in theory, how would this work? I think that's doable. It's not super hard, but the amount of code is quite a bit, and it's also quite easy to find, like, it's super easy to have a bug anywhere here. And like if you didn't have this helper function, which is kind of hard to make in 45 minutes, you're going to have like 80 lines of code along with thinking about it. So I definitely think this is like outside the realm of something. I think people were posting in the comments, if I was asked this in an actual Amazon interview, like I would probably want to leave. So, and it's like people at Amazon are smart, but like, yeah, because I think this is just, it's not like a super hard problem. It just takes like a really long time to get everything right. Okay, so let's think about the time and space complexity here. Like I'd say as far as like a hard versus super hard or whatever, I'd say it's like a medium hard, but the amount of time to write the code is like a very hard. Because yeah, like you have to remember a union find, which I do remember, but I can't write it super fast. Like I have to constantly think like, okay, like what are these things supposed to be? And then I'd have to like double check it and stuff. But yeah, I would encourage you to pretty much memorize union find, I'd say. Yeah, because it's very helpful for like a lot of problems where like without it, you're pretty screwed. So it's definitely one of those, like, if you have extra time, do it. It's not like a priority, but it's definitely one of those like union find, try type of things where like for some problems, it is basically the only way to do it. So if you have the time, definitely learn it. But yeah, so let's go through the time and space. So for union find, so n is going to be the length of the number of nodes, right? Yeah, so n is the number of nodes. And then the number of edges, we can actually check like our constraints here. Actually, we can check our constraints here just to double check. Yeah, so our number of edges is min 200 and max 4000, but whatever. We'll just say E and V, where V is the, as always in a graph, V is the vertices and E is the edges. So for the time, constructing a union find takes nothing. Find and union should theoretically be a O of 1. Theoretically, they're a little slower, but close enough. Okay, so for this Kruskal takes O of n time. Like every time you run it, it takes O of n because you're essentially running through every single edge. So that's O of E. And then you are running it. So also, yeah, for this part, it doesn't cost you anything. Sorting is n log n, which is going to be cheaper than the other stuff. Kruskal is also O of E, I guess. But this is the part that costs the most. So this is E squared, because you're doing this twice. And then technically you are like making all of these. So I guess making all of these would also be like, let's just call that V or something. And you are also making all of them. And then you are, yeah, you're making all of them. And then you might have a lot of them. I think it's O of V anyway. Yeah. Making an array. Actually, no. I guess this would be O of 1. This would be O of this. Yeah, making it would be O of 1 space, or sorry, O of 1 time, but O of V space. But yeah, I'm not sure if you need this V or not. But either way, like this E squared is more often than not, like E is already twice as big as V, and it's squared, so V is pretty much negligible here. And space. So for space, this is O of V, right? For the parents and the ranks, like you can have v amount, and then we do add an edge to the edges, but it's in place, so I don't know if you want to count that or not. Like we do technically add an edge, but it's in place. And then as far as this, and yeah, also this critical and pseudo critical is part of our result. So you could argue this is O of V because essentially you're just adding to the edges in place that are already there. I mean, I guess you're adding like one variable to them. So I think it would be, yeah, I think you are still adding a variable to all of them. So it still would be something like V plus E actually, because even if it's in place, you're still adding like a number to all of them, and that would be E. But yeah, I think the space is V plus E. I think time E squared or E squared plus V. I don't think you need it plus V, but either way, like I said, this is like tops off at 4,000 and the number of nodes is like 100 or something, so that doesn't really matter. But yeah, that's going to be it for this problem. Quite a long one. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.